All right, cool. Welcome everyone. For those of you who didn't meet me last week, I'm Mario. I just started my PhD in Oxford, so I spend my whole day doing fun maths, and I'm going to tell you a bit about some of those maths. Before I start, basically, if you have any questions at any point, feel free to put them in the chat. I have it in front of me, so I'll be able to read them. And I also probably ask you questions as well, and I would really appreciate your input on that. So just to get us started, just so I have an idea. So we're going to be talking about cryptography as a means to introducing some basic concepts in number theory and elliptic curves and geometry. So has any of you heard of any of these topics before? And if so, which ones? This also gives me a chance to see that the chat is working. No, great. Then you're going to learn a lot today. All right, cool. Some people yes, some people no. So I'll just very little. Cool. All right. Well, hopefully you learn a lot today. So yeah, as I said, any questions you have at any point, do let me know. So just in case someone doesn't know what the word cryptography means, cryptography is about encoding and decoding messages. So it's something, well, particularly relevant with all of the technology that goes on nowadays. So basically, the basic idea is if I want to transmit a message to someone else, this might be like credit card details, for example, and I don't want anyone who's not supposed to have access to those details to be able to see that, then basically, how do I do it? Um, and there's a lot of maths involved in all of these processes. And so I'm going to try and look at two different examples of how maths can help to do this, one based on number theory and the other one based on elliptic curves. But before that, basically, I want to start by saying a bit of how this general framework basically works. So I guess from like cryptography has been around for many, many years. And I guess you can have some of the very basic procedures, right? If you have some sort of message that you want to decode, you can just sort of have some sort of cheat sheet where every letter is associated to some other letter, and then these are called substitution ciphers, and then you just sort of follow that rule, and then you start with a message that makes sense, you turn it into something that sounds gibberish, and then if you want, you can do the process back and then recover the message. This is quite simple. It's called Caesar cipher or substitution cipher. Um, and it has the advantage of it being quite simple, but the problem is that it's not very good because first of all, there's not very many possibilities of how you can do these substitutions. And so you can just brute force it and eventually you'll get a message. But then you can also do some sort of more sophisticated techniques, such as, for example, there's this thing called statistical analysis or frequency analysis of like in the English language, not every letter appears as frequent in every single word. So for example, if you have some sort of message, you can just say, oh, in this encrypted message, the W seems to appear a lot. And so you can sort of compare the frequencies of your encrypted message with the sort of average frequencies that letters appear in the English language. And by doing that, it's actually very easy to sort of see how you map out each letter to another letter. So obviously they just were in the past. Now we have computers. This sort of encryption method doesn't really work anymore because they're very easy to break. So we need to do something that's slightly more clever, right? And so the basic framework is the following. Suppose that we've got two people, Alice and Bob, they want to communicate. Alice has some sort of secret that they need to pass to Bob. How can they do it so that any other third person, Eve, just doesn't have access to it? So there's a very cute way of doing this using this method of double locking. So you just use two locks. And so imagine you have some sort of box where you're putting your message in and you want to send this to Bob. So what you can do is you can put your message inside of the box and then you lock it with your own lock and you keep your key. And you can send that to Bob. Well, it's kind of useless for Bob now because he obviously doesn't have the key to your lock. So he cannot open the box. But what he can do is he can put another lock, right? So he's going to double lock that box and then keep his own key. Now Bob can send this back to Alice, who can then take out her own lock. Right now, Alice can no longer open the box because it still has Bob locks on, but now she can send it back to Bob, who can now remove the other lock, and then Bob can see the message. And every single time that this box has been passed around, it's always had at least one lock put on, and Eve doesn't have the keys to either lock, right? So this sort of way of passing around locks and boxes means that Alice can send a message securely to Bob. Does that make sense? How that sort of works? Uh, you just say yes or no in the chat. That'd be yes. Okay, cool. Um, so obviously that's very cool. it's slightly overcomplicated. So here's an easier way of doing it, and this is known as public key cryptography, where basically what happens is that suppose that you want to send some message to Bob. Well, Bob, who's the person receiving it, can just send you the lock, right? That makes it a lot easier. Now, it means that he can just put a lock out there. Anyone who wants to send Bob a message, all they need to do is they need to take Bob's lock, they put it on the message, and then they send it back to Bob, right? Now, because Bob is the only person who has access to the key to that lock, he can unlock that and open the secret. So this is the basic way that cryptography works, or at least public key cryptography. And so this is what many of the modern day algorithms use, is this quite simple idea. Now, for all of these things to work, however, it's important to have really good locks, right? And this is where the mathematics comes in. So what do we want from a lock? Well, we want it to be something that is, first of all, easy to use in one direction. So Bob is just going to put a lock out there, and anyone with access to that lock should be able to use it to lock some sort of message, right? So locking the lock should be really easy. However, we want unlocking the lock to be something really hard, right? Because we don't want anyone to be able to unlock it. We just want just Bob to be able to do that, right? And so these sort of, we don't use physical locks, of course, because a lot of this communication happens online. What we use is something that's called trapdoor functions. And these are sort of algorithms that are really easy to do one way, namely it's really easy to close the lock, but they're really hard to do the other way, right? So if we want to open the lock, that's actually really quite hard. So that's where the math comes in. And in particular, I'm going to try to show you two examples of such trapdoor functions. They're not easy functions, however, so we need to do a bit of maths before we can get there. And so the first trapdoor function I'm going to show you relies on something which is called modular arithmetic, which possibly many of you, or at least some of you, might have heard before. And so modular arithmetic is basically the study of remainders. And it's a way of dealing with really large numbers when all we care about is actually quite small information. So a basic example of this is, for example, suppose that I say, I don't know, it's 4 p.m. now. What time will it be in 40 hours time? Well, it's not going to be 44 p.m. That's not really how hours work, right? So then how can we figure this out? Well, one thing you can do is you can say, well, it's going to be 4 plus 40, but then I'm going to subtract however many multiples of 24 I need, so that because 24 would be like a whole day, right? And so if we do that, well, 4 can be like, what, 16, and then, so that's 16 p.m. really. Then we add 40 to it, that gives us 56, and then I need to subtract 24, that gives us 32, but oh, I need to do it again, so another 24, that gives us 8 a.m., right? So 40 hours after 4 p.m. will just be 8 a.m. in a couple of days' time. But if we don't really care about the day, we can see that in a way, what we've done here is said that 4 plus 40 is 8. It can seem a bit of nonsense if you just write it down, but of course it makes sense because days sort of go back after 24 hours. Another example of this is when we are adding odd and even numbers. So I can give you two really, really large numbers and ask you to tell me whether the sum of them is odd or even. Well, you don't really need to actually add the numbers to find out whether the answer is odd or even. All you need to do is check whether each of the numbers is odd or even, and then you know the basic rules of how to compute with that, right? So if you add two even numbers together, you get even. If you add two odd numbers together, you get even. And if you add one of each, then you get odd, right? So this really is what modular arithmetic is. But obviously in maths, we want to make things precise. So I'm going to actually give you a definition. So we say that two numbers, say A and B, are congruent modulo n if they differ by a multiple of n. And so we write this as A is congruent, which is this 3, it's like an equal sign with an extra bar, modulo n in brackets, right? So just to give you some examples about how this works, so we have for example, 3 and 5 are congruent modulo 2. So we say that two numbers are congruent modulo 2 if they differ by an even number, namely if they have the same parity, right? So any odd number is going to be congruent to any odd number, and every even number is going to be congruent to an even number, but no odd number can be congruent to an even number modulo 2. Does that make sense? If so, can someone give me another example of two numbers which are congruent modulo their favorite thing? All right, yeah. So here's some more examples. So we can say 4 is congruent to 7 mod 3 because they differ by a multiple of 3. And then Because 6 and 13 mod 7, because they're both different by a multiple of 7. And you shouldn't even be scared of just using positive numbers. We can do the same trick for negative numbers as well. And we can say that this is even congruent to -1, right? Because 6 and -1 divided by 7, which is a multiple of 7. Okay, and so the point is, as I was saying before, this is very useful when we're dealing with computations with really large numbers. And you can probably see how in cryptography, it's very easy to quickly go to really large numbers. And so this is going to be a very useful thing. So for example, if I tell you that I have one number that's 1 more than a multiple of 3, and I'm adding it to a number that's 2 more than a multiple of 3, what is the outcome going to be in relation to a multiple of 3? So I'll just say it again. If you're adding two numbers together, one of which is 1 more than a multiple of 3, i.e. congruent to 1 mod 3, and another number which is 2 more than a multiple of 3, i.e. congruent to 2 mod 3, what can you say about the sum? The sum is going to be a multiple of 3, yeah. And someone's written it sort of using algebra, right? So if we have a number which is 1 more than a multiple of 3, that means that we can essentially write it as 3n plus 1. If we have some other number which is 2 more than a multiple of 3, we can write it as 3n plus 2. And so, well, what can we say about the total sum? Well, this is going to be 3 times n plus 1, which, oh, look, it's a multiple of 3, right? And I didn't tell you what the numbers were. Just knowing the remainders allows you to deduce the remainder of the sum. And it works essentially the same way for multiplication as well. So I think it's good to sort of try and see how you would write this down mathematically. So what does this mean? It means that if you have two numbers, so you have a number x and number y, and you know the remainders when divided by some number n. So suppose that x leaves remainder r when divided by n. We write this as x is congruent to r mod n, and y leaves remainder s when divided by the same number n. Then what can we say about x plus y? And what can we say about x times y? Well, x plus y is going to be congruent to, well, r plus s mod n. And x times y is going to be congruent to r times s mod n. Right, so we sort of have that the numbers modulo n still sort of respect addition and multiplication as we expect them to. Does this make sense? Are there any questions about this so far? Are r plus s multiplied with mod n or only the s? So this number might not be the remainder. I think this is what question means. So for example, suppose that you have x being congruent to 2 mod 3, and you have y being congruent to 2 mod 3. Then what can we say about xy? Well, xy is going to be congruent to 2 times 2 mod 3, which is 4. But 4 is also congruent to 1 mod 3, right? So if we multiply two numbers, which are 2 more than a multiple of 3, the outcome that we get is 1 more than a multiple of 3, right? So the R and S, you can multiply them normally and then sort of reduce them mod 3 again. Hopefully that makes sense. Okay, cool. So let's just play around with this and try and spot some patterns because there's quite a few cool patterns in this. So here's a table of numbers. So just to tell you what I've done here. So I'm looking here at numbers modulo 15. So this table is modulo 15, right? So every integer modulo 15 is going to leave remainder 0, 1, 2, all the way up to 14. This is the possible remainders that a number can have. And then the question is, well, how about its powers? So if I have a number which is 0 modulo 15, namely it's a multiple of 15 and I square it, it's still a multiple of 15. So the remainder is still 0. If I cube it, it's still a multiple of 15, remainder 0. So that's why the first column here is all zeros. If I have a number which is 1 more than a multiple of 15 and I square it, well, what we've learned is that we can just multiply the remainders together to obtain the remainder of the square. And so that means that the remainder of a number which is 1 more than a multiple of 15 squared is simply 1 squared modulo 15, which is 1. Same for cubes, same for fourth powers, and so on. And so I've done basically the same with every other number in this table. And my question to you is, Can you see any patterns? Can you spot anything here? Okay, so 6 is always in the sixth column. Yeah, exactly. So maybe let's try and see why that is. Well, if I square 6 squared is 36, but I'm working modulo 15 and 30 is a multiple of 15, so I actually get back 6. Now to go from one row to the next, I'm just multiplying by the same number again. So it seems like I'm just going to get 6 over and over and over and over. And something similar happens with 10, because 10 squared is 100, and 90 is a multiple of 15. Um, so there's something funny going on about the columns of 6 and 10. I agree. And someone's asking, why is 3 to the power of 5 3? Okay, well, I mean, maybe I've made a mistake. That's possible. But so 3 squared is 9. Now, 9 times 3 is 27, but modulo 15, we can subtract 27 leaves remainder 12 modulo 15. So that's why a cubed, 3 cubed is congruent to 12. Now, to obtain 3 to the power 4, I just need to multiply this 12 again by 3. That gives me a 36. And again, 30 is a multiple of 15, so that leaves the remainder 6. To obtain the next row, then I just multiply by 3 again. 3 times 6 is 18. 18 is 3 more than a multiple of 15, so 3 to the power 5 is 3. Hopefully that answers your question. Yeah, there's also something going on about 5. So you seem to be pointing out a lot of things about these columns, right? So column 5, column 6, column 10 if you want. Column 3, these look kind of weird. Someone's saying each column has a repeating sequence. That's very much seems to be the case. So what can you tell me about the columns that no one said anything about? So someone's commenting most columns only contain multiples of A and then 1. So that is correct. Column 13 and 7 seem to break the pattern. Yeah. So these are actually the interesting columns. So what actually is going on in columns 13 and 7? Okay, someone's saying 13 and 7 are prime numbers, but then 11 is also a prime number, so why doesn't it do the same? Okay, I guess what exactly do we mean by the same? Well, I can see some things in common between column 7, 11, and 13, right? In fact, I can see something in common about all of these columns. So we seem to have split the columns into two groups. Right, I get 0 as well. So what is the difference between, so someone's saying, yeah, 1 is in the same places. That seems to be interesting. What's going on in row A to the 4? So my next question is, what is the difference between the columns that I've marked with an arrow at the top and the columns that I've marked with an arrow below? Someone's saying they rotate through patterns of 1, 2, or 4 values, I believe. Yep, that very much seems to be the case. Someone's saying below starts with 1. Yeah, then by 1 you mean, by starts with 1 and you mean ends with 1 if you look at the column from top to bottom. The ones marked with an arrow at the top don't contain 1. Yeah, exactly. So that actually is going to be a super important observation. So you're going to see in a second why ones are very useful. And that is the key observation. So how, like, can anyone find a pattern of which colors are marked above and which colors are marked below? So what is different from the numbers 0, 3, 5, 6, 9, 10, 12, and the numbers at the bottom? So 1, 2, 4, 7, 8, 11, 14. Yeah, so someone's saying the ones at the top have factors of 15, or they have factors that are factors of 15. So a different way of saying that is that they share some prime factor with 15. Whereas the numbers that are marked at the bottom do not share any prime factors with 15, and these numbers are called coprime. So if you have two numbers which don't share any prime factors with each other, like for example 5 and 6, um, these numbers are called coprime. And so the numbers that I've marked at the bottom are those numbers which are coprime to 15. Whereas the numbers that I've marked at the top are those numbers which are not coprime to 15, i.e. they share some common factor with 15. Okay, before I explain this a bit more, another cool fact that I'm not sure, sorry if someone's mentioned it and I didn't see it, is that if you look at the row 8 to the 5th, well, this row is just the exact same row as the first row. Which is a cool fact. And also all of these things, they seem to be true, but I guess the question is, why are they true? And as a homework, if you want, you can try and prove that all of these things are actually the case. But for now, I'm going to try and write down a precise statement, which is known as Euler's theorem, which is true in much more generality, and is really what is the key of this first trapdoor function that I was talking about. And so the statement goes as follows. It says, well, suppose that you have two primes, P and Q. In our example here, these primes are 3 and 5, which are the prime factors of 15. So suppose you have P and Q be distinct primes. And we're going to take a number A, which is co-prime to P and Q. So let A be co-prime, namely it doesn't share any factors with PQ. Be co-prime to P and Q. Then what we observe is that if we raise A to some power, we get back to 1 modulo PQ. Right? And if you see, this is actually what's causing this repeating patterns that you see all the time, right? Because that's what we want. We want the fact that if I keep finding powers and powers of A, eventually I sort of loop back and go back to the start. That is a useful observation here. And so the key is, well, what is this repeating pattern, right? And well, some of these columns seem to have a repeating pattern of 1, some, like for example 1. Some of these columns seem to have a repeating pattern of 2, like for example 11. Some of these seem to have a repeating pattern of 4, for example, I believe 2. But the point is that actually, if we look at P minus 1 times Q minus 1, that is always at least a repeating pattern. So what Euler's theorem says is that if we look at P minus 1 times Q minus 1, that will always give us a repeating pattern. And so in the example that we had below, P was 3, Q was 5, P minus 1 is 2, Q minus 1 is 4, and 2 times 4 is 8. Surprise, surprise, that's why I chosen 8. Now someone's saying, do similar patterns emerge if you use another modulo, like for example, modulo 8, which in this case, I guess, is not a product of distinct primes? The answer is yes. There is always some sort of repeating pattern if you look at the powers of a coprime number. So this is also included in a more general version of Euler's theorem, and if you're interested in that, then definitely take a look at it. But for today, all we're going to use is this statement below here, which is that if I have two distinct primes and I look at numbers modulo their product, then they have the powers have a repeating pattern with period P minus 1 times Q minus 1. Okay. Are there any questions about this? Or does this make sense? Okay. No questions. So that means that I finally get to tell you about the first trapdoor function that we're going to be looking at. And this is now as the RSA algorithm. So basically, this is going to use what we just did with Euler's theorem to give us an actual method of sort of encrypting and decrypting a number. So let's go through how this works step by step. So the first thing that we need to do is we need to pick some really big prime numbers. And the point of picking big prime numbers is that the problem that is really hard to do is factoring numbers, right? A computer is still really, really bad at factoring really large numbers. I mean, obviously, if you have a really large number, but all of their factors on 2 or 3, then you will eventually be able to do it because a computer is not bad at spotting that a number is even, or even that a number is a multiple of 3. Just add the digits and check if it's a multiple of 3. So you can sort of little by little peel off factors of 2 and 3 and then decrease the size of the number. However, if we have a number which is made of 2 really, really large prime factors, that is actually going to be really hard to factor. And that is important. So we're going to pick 2 prime numbers, which are very large. Obviously, my computational skills only go so far. So unfortunately, I'm going to take my prime numbers to be 3 and 7. That's about as large as I can confidently do the calculations here. And then, but you should imagine that if a computer is actually doing this, they're going to pick some incredibly big prime numbers. And then we consider n, which in this case is 3 times 7, which is 21. Now, the whole point of this is to be able to transmit some sort of message. Now, a message, you can think of it, maybe it's a word, but we're going to think of it as a number. And there are many ways that you can transform a word into numbers, right? You can say, for example, I don't know, just label the alphabet, right? A is 1, B is 2, C is 3, and you sort of put them together in a string of numbers. So by doing your favorite procedure, you can turn whichever message into just some numbers. And then the point of this is we want to actually send out this important number across. So how are we going to do this? Well, what's our log? So our log is going to be some number that we call E. And this log is just, we just need to pick something which is co-prime to our number n. So in this case, I'm going to pick E, which is our log, to be equal to 5. And say that there's some message that we want to transmit. And suppose that we're being simple and the message we want to transmit is just a number 2. Right? In practice, it would be something much bigger, but for simplicity, let's just keep it this way. Okay, so I know the message and I want Bob to be able to receive this message, but I don't want anyone to be able to intercept it. How do I encrypt the number? Well, the way it works is I'm just going to raise 2 to the power of E and then take it modulo n. So I do 2 to the power of E, which is 2 to the power of 5. This is 32. And then I just reduce it modulo 21, which gives me 11. Right? So this is equal to 11 modulo 21. And so what this means is that the number that I'm actually going to send out is just 11. So then Eve might receive the number 11, but all of the information it has is N and E, and it's not really possible to recover 2 from that. You would need to be able to take like a 5th root of 11, which is in practice really, really hard. This is a really hard problem. And so essentially she cannot do it. But now Bob is receiving this number. Well, how can you actually decrypt this message? So the idea is that you look for a number D with the property that E times D needs to be 1 more than a multiple of P minus 1 and Q minus 1. And I'll tell you in a second why this is what we want. Times Q minus 1. So in our example, this would be 2 times 6, which is 12. Right? Now we know that the powers of 2 repeat every 12. So if I can find a number D with this property here, then by raising 2 to the 5, i.e. 11 to the power of D, I'm going to be able to loop back. Let's actually do the math because it's way easier to understand than with the words. So first of all, we know that E is 5. So we need to find a number D such that 5D is congruent to 1 mod 12. So what this means is that we need to now look at multiples of 12 and look at something and add 1 to get a multiple of 5. So in fact, the one that works is if we take, for example, D equals 5, then I think this works, right? Because we have now 5 times 5, which is congruent to 1, which is, 5 times 5 is 25, which is 24, which is a multiple of 12 plus 1. So we have this extra 1. So in this case, our decryption number is going to be equal to 5. Now, suppose that we have our message 11. If we want to decrypt it, all we need to do is just raise it to the power of 5 again. So we start with 11, we raise it to the power of 5, and then if we actually do the maths, and obviously a computer can do this really easily, then we're going to see that we're going to end up back with 2. Now let's try and, instead of doing the computation, let's try and see mathematically why this actually works. So recall that what we did originally was you take the number 2 and we encrypted it, meaning we raised it to the power of 5. Now to decrypt it, we're saying that we just need to raise it to the power of 5 again. And the question is, well, why does this work? Well, it's because 2 to the power of 5 to the power of 5 again is simply 2 to the power of 5 times 5. But 5 times 5 is 25. So this is just 2 to the power of 25. Now we know from Euler's theorem from before that the powers of 2 repeat every 12, which means that 2 to the 25 is going to be the same as 2 to the 25 minus 12, and it's going to be the same as 2 to the 25 minus 12 minus 12, right? So in particular, it's 2 to the 25 minus 12 minus 12, but that's just simply 2 to the 1, and 2 to the 1 is just equal to 2. Right? So this procedure basically allows us to encrypt a number, and then by raising it even more, loop all the way back around to the original message. And so in this way, we've decrypted our original message was just 2. Modulo 12. Okay. Does this make sense? Yes. Okay, cool. So this is quite a simple, well, relatively simple algorithm. But it relies on the existence, as someone's pointed out, of large prime factors. And also, this problem has been around for ages. So computers now, they do have better and better algorithms to be able to factor out large numbers. So instead, there is an even better algorithm using something called elliptic curves that does this in an even more secure way. And so that's what I'm going to talk a bit more about now. So I guess the first thing is, I don't know if any of you have heard of the word elliptic curves before. There's nothing really to be scared about. An elliptic curve is just a graph that has this very specific form. So it's a graph of the form y squared equals some sort of cubic with no x squared term. So a and b here can be any positive integers, whatever you want. They can even be 0 if you want. And I guess I've sort of graphed 3 different elliptic curves for different values of a and b. So you can think of this, if you think of what just a cubic of the form x cubed plus ax plus b looks like, well, it's going to go to infinity as x goes really large. It's going to go to minus infinity as x go really large and negative. And then in between, it's going to have 2 turning points. Right now, there's 3 options. Either the 2 turning points are above the x-axis, either they're both below the x-axis, or you can have one above and one below. Right? And then if you try and grab the square root of this graph, then it really matters whether they're above or below, because everything that's below the x-axis, namely it's negative, is going to disappear when you take the square root, because there's no values that you cannot really take the square root of a negative number. And so these are the 3 cases represented here. The first one is where the 2 turning points are above the axis. The second one is when you have one above and one below. And then the third one is when both of them are below the x-axis. And so this is basically what an elliptic curve looks like. And the reason why it's important is because we can use them to have some sort of like algebraic structure. So basically we can take 2 points on an elliptic curve and sort of add them together to obtain a new point. And this might sound like it's something silly to do, but it's actually really, really useful. And I'm going to show you first how we do this point addition elliptic curves. So I've drawn here some elliptic curve, and it has sort of 6 points in it. So this, if you are interested, this elliptic curve is actually nothing else than y squared equals x cubed plus 1. And so this is what the graph looks like. And suppose I take 2 points on this elliptic curve. Let's call them P and Q. Say that is point P and that is point Q. We can add these 2 points, and obtain a third point as follows. So what we do is we draw the line that goes to the points P and Q. Now, this line is going to intersect an elliptic curve at some of the third point, right? Which we can call, say, P star Q. Right, so this is the third point of intersection of the line that goes through P and Q with our elliptic curve. And now the next thing that we're going to do is reflect it along the y-axis. And this reflection is what we call P plus Q. Right? So I guess something to point out is if you look at the equation of the graph, it's invariant that it's substituting y and minus y, namely it's an even function of y. And so in particular, the graph is always going to be symmetric with respect to the x-axis. So that is essentially, we have 2 points P and Q, we draw the line between them, that gives us a third point. Now we reflect it, that gives us a fourth point, and this fourth point is what we call the sum. Now, what is all this nonsense about sum? Well, it turns out that actually this satisfies the properties that we expect addition of numbers to satisfy. In particular, we can show that P plus Q is the same as Q plus P, so addition is commutative. We can show that addition is associative, namely if we have P plus Q and then a third point R, that's the same thing as doing P plus and then the addition of 2 points Q plus R. So in a way, this gives us a geometric way of adding things. So previously we were using numbers, now we have geometry in a way. And this is a much harder problem because the addition here is much harder than addition in numbers. This is going to give us a much more complicated problem that is going to be good for what we're intending to do. Okay, someone's saying, how are you adding the points? So what I mean by adding the points is as follows. Let's do another example. Suppose now that I want to add, say, I don't know, this point over here, P plus Q, to some other point R. Right, so let's call that point R. So how would I add these 2 points? Well, so what you do is you draw the line through the 2 points that you're trying to add. That means you draw the line between R and P plus Q. That's going to intersect your elliptic curve at some other point, which in this case is P. Yeah? And then you reflect P along the x-axis, which in this case is going to stay put. And that is what you're calling the addition of these 2 points. So in this case, if we add P plus Q to R, we just get back the point P. Yeah? Okay, now why do we call this process addition if it has nothing to do with actual addition of numbers? The reason why we call it addition is because it behaves in the same way as addition of numbers does, right? So it will satisfy the same properties. And so from a mathematically abstract point of view, it really is the same thing. So this is something that if you study maths, you'll meet in first year. There's this concept of a group. And there's, I guess, if you came to the talk last Tuesday, you saw the fundamental group, which is another example of things that we can add things, right? We can add loops. So in this case, we can add points and we can add numbers. And all of these different abstract concepts sort of respect the same rules in a way. So I'm calling it addition and using the same symbol, but really it has nothing to do with, I'm not adding the coordinates of the points or something like that. If you take 2 points and add the coordinates, chances are that point is not going to lie on your elliptic curve again. So that's sort of like not very useful. But this is a way of adding 2 points in some abstract way and getting a third point. So all I mean by addition is that it takes in 2 points and produces a third point, and we call that third point the sum of the previous 2, right? But this is just some sort of name. If you don't like calling it addition, you can call it whatever you want. You can say, I don't know, it's the convolution of P and Q, or pick your favorite word for it. And we can do something even better because we can also add a point to itself. So if we want to add a point P to a point P, then what the recipe says is, well, draw the line between P and P. But there's infinitely many lines between P and P. So what we do is, if you imagine sort of having 2 points and bringing them closer and closer and closer together, the line between the 2 points becomes the tangent to the curve. And so if we want to add a point P to itself, all we need to do is just draw the tangent line, right? So let's just do an example. So for example, if you take this point here, let's call it maybe S, right? If I want to add it to itself, namely compute S plus S or 2S, right? Which would be the same thing. What do? Well, I draw the tangent line to S. This is going to intersect the curve at some other point, in this case R, and then I reflect it along the y-axis, and that gives us a point Q. So 2s in particular is equal to q. Yeah, and if you wanted, you could write down explicit formulas for these things, right? You've probably seen in school, if you have y squared equals some cubic, you can, and 2 points, you can write down the equation of the line between those 2 points, you can find the intersection of that line with the cubic, and then you can reflect it. All these things are things that you can do, and you know that this actually works. And it's going to give you some sort of formula. You can also just plug in the numbers and works. That is what you have a computer do. Now, someone's saying, what if the tangent doesn't touch the ellipse or the elliptic curve? Okay, so that is something that can happen. So what would happen if you try add the point p to itself? That's a great question. Well, in this case, we need to get a bit creative. And the way that mathematicians have solved this is to say, well, there is an extra point of this elliptic curve which I've not really graphed in the equation, and that's the point infinity comma infinity. So if you imagine plugging in x equals infinity, infinity cubed is infinity. If you add a lots of infinity, that still gives you infinity. If you add b is infinity. And y squared is also infinity, right? So you have this sort of weird point infinity comma infinity, right? That is satisfies the equation in a way. And so we call that, surprisingly, the point at infinity. We call it O. And then if we ever run into the situation where a line doesn't intersect back a curve, we just say that they intersect at infinity. And that's what's really happening at P. So if you look at P and you try and draw the tangent line, well, that obviously doesn't intersect the curve again. So we just say, well, it just sort of intersects it at infinity, right? You're just not really going far enough. And so that's what we would do. Now, someone's asking, what would happen if you did s plus s plus s? Well, let's do it. So we've done s plus s and we've got in q. So all we need to do now is to add s to q. So if we wanted to compute 3s, well, how do we do that? Well, we just need to add 2s, which is q, 2s again. Let's add q and s again. So q plus s, we draw the line. That gives us p. Now we reflect p. It stays back at p. So that gives us p. Right? So 3s is equal to p. And we can keep playing this game. Well, what happens if we want to compute now 4s? 4s gives us p plus s, right? This intersects the curve again at q. We reflect it. That gives us r. So this will be r. Let's keep going. What about 5s? So 5s is just r plus s. Now, if we want to add r plus s, now this gets tricky. If you look at it, the line through r and s is tangent to s at that point. And so in particular, we think of S as being some sort of double point, right? It's like 2 copies of S really put together. And so the third intersection of the line with R and S is again S. Now, if we reflect it, that gives us a point here at the bottom, which let's call it maybe T. And then if you want, you can keep going. This would be T plus S. And then if you do this, you'll get that actually the line through T and S doesn't intersect the curve again. So it intersects it at infinity. And so 6s is equal to the point at infinity. Okay. What if the tangent at P is perfectly vertical? Can you still say that intersects the curve at infinity? Yes, exactly. That's the point. So if it doesn't intersect the curve, then we just say that the intersection is somewhere at infinity. And so as you can see, we've started with a point S, and we've done something quite similar as before, right? We start S, we add it to itself, we get Q, we add it again, P, then R, then T, then O at infinity. What happens if we add S again? You're going to get back to S. So if you keep adding S to itself, you sort of run back all the way up and then go back to S, and then you just keep getting these sort of cycles, which is very similar to what we had before, right? And so these sort of cycles is what we use in elliptic curve cryptography. And so the way that this new trapdoor function works is essentially as follows. So say Alice and Bob are going to agree on some elliptic curve. Say, I don't know, for example, you can take something to be y squared equals x cubed plus x squared plus x plus 1. Some prime number p, which say it can be something like 97, and you can pick a point p, say which is, I don't know, the point 720. And now, because we don't want the numbers to get too big, basically what I'm doing is I'm just looking at points that satisfy this equation modulo p. So in this case, if you try and do the calculation, 7 cubed plus 7 squared plus 7 plus 1 is going to be congruent to 20 squared, which is 400 modulo p. And this idea of doing the modulo p is just so the numbers don't really get too big, but you shouldn't worry too much about it. So I should probably make a difference what's big P and what is little p. So all of this information is sort of public and everyone has this information. Now, the way we can communicate a secret message is as follows. Alice and Bob are going to pick their favorite numbers and keep them secret. So Alice is going to pick some number A and Bob is going to pick some number little b. Now, Alice and Bob are both going to they're going to take the point P, add it to itself A times and send that to B. Bob is going to take the point P, add it to itself B times and send that to Eve. So then now AP and BP is some sort of point that everyone has, right? Now, how can Alice and Bob use this to agree on some sort of code? Well, Alice has BP because Bob has made it public. And so Alice can just add the point BP to itself A times to obtain the point ABP, right? So Alice then can compute ABP and Bob they can compute it from BP. Bob can take the number AP that Alice has calculated and compute the number ABP, sorry, the point ABP by doing, I guess it's the same as BAP, by adding the point AP to itself B times, right? And so what this means is that both Alice and Bob are now able to compute this magic point, ABP, but Eve can't, because all the information that Eve has is the value of AP and the value of BP, right? And so in practice, it's very hard to go back from AP and find the value of A. So like, for example, if I told you, let's see, I think I have an example here. So if I told you that AP is equal to 1746, the only way that Eve has of finding out what the value of A is to try and add the point P to itself many, 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 many times until you somehow magically hope to get this point. Now, I think the answer in this case turns out that A is equal to 47, right? And so if you, instead of these small numbers, pick some really, really large numbers, this is an impossible problem to do in practice because a computer will just not be able to do it quick enough. And so essentially what the outcome of this algorithm does is it allows Alice and Bob to somehow share some sort of information, this ABP, and then anyone in between who's been hearing and intercepting these messages cannot really have access to this information. Now, how can they use this? Well, if they know the coordinates of these 2 points, ABP and ABP, they can say, for example, look at the X coordinate, this is going to be some number, and then maybe they can use this as a key to something else and some other sort of algorithm. But the point of this algorithm is that it's allowing Alice and Bob to agree on some common code, password if you want, without anyone else being able to intercept it.